In this lesson, we're going to focus on working two different types of two-part problems. The first two-part problem is the same as the ones we've worked in the past. We have two moving objects, and those two moving objects are each going to have their own equation or set of equations describing their motion, and then we need to figure out how to put those two equations together to figure out something about this system of two moving objects. We're actually going to start off by reviewing by working a problem like that. But we're also going to learn that there's another type of two-part problem called a two-dimensional problem, and we're going to work one of those at the end of this lesson. Pay attention to the differences between these two types of two-part problems and what's unique to two-dimensional problems. Okay, let's start off with a review question about a two-object two-part problem. So here we have two students deciding to race their bikes. And the first student is able to accelerate at 0.5 meters per second squared, the second at 0.75 meters per second squared. So obviously the first student, if they both start at the same time from the same place, the first student is obviously going to lose. However, to make things interesting, the first student is given a head start of 2 seconds. Who will win if the race distance is 25 meters? Now, just like many physics problems, there are multiple ways to solve this problem. One way I could do this is find out how long it takes the first student to get to 25 meters, how long it takes the second student to get to 25 meters, and then the one that takes longer loses the race. That's an option. Another way for me to do this is to find where the two students actually meet and then see if that happens before or after 25 meters. And if it's before 25 meters, then I know that the second student will win. And if it's after 25 meters where they meet, I know that the first student will win. Now, if you don't really believe me or you can't picture what's happening there, just wait until you see this graphically and that will make sense to you. I like that second solution method better, maybe because it's a little more interesting to find out where the students actually do meet, because graphically I'm going to be able to observe some trends and check how things are going, if I'm using the equations correctly, if things fit together as expected. So that's the way I'm going to do it. Now I'm going to need to start with a plan for solving this two-part problem. And the plan is to find a kinematics equation describing the motion of each object. So I'm going to have sometimes two separate kinematics equations, sometimes it's just two of the same kinematics equations with different values plugged in. Because I have two accelerating students on bicycles, I'm probably going to use the same kinematics equation for position and acceleration. Then if the two objects pass, at that point I need to keep in mind x and t are going to be the same for both of the objects or both of the people. Right? And then lastly, I'm going to use substitution to combine the equations and solve for an unknown. If I were to sketch out this problem, this is what it would look like. I'm going to do this on a position time graph, and position time with acceleration means that I'm going to have parabolic curves. The first curve for the student with a head start is going to be connecting 0, 0 to some time and some position that I don't know from the problem. Now, just to repeat this for emphasis, I know I'm given a 25 meter value in the problem. That seems like it should get plugged in somewhere. But keep in mind, in these graphs, I'm finding where these students pass one another. And that's not going to happen at 25 meters necessarily. So I just have to work this problem out and find the meeting point distance and then compare it to that 25 meters later. So this would be the curve for the student with the head start. And interestingly, you might be thinking to yourself, well, how can the student with the head start at time 0? Wouldn't the student with the head start at a different time because we're giving them a head start? Like, wouldn't it be -2 seconds because they're starting ahead of the other student? Yes, that would work as well. It doesn't really matter whether you start at 0, 0 for this student or -2, 0. As long as the other student starts 2 seconds later. So what's the other student's curve going to look like if my head start student starts at 0, 0? Well, that student is going to start at the same starting spot, the same 0, but at 2 seconds. And that student is going to travel and meet at the same time and position point as the first student reaches. So they're going to pass one another eventually. I've labeled this student student B. And I know if student B is accelerating more quickly than student A, eventually, even if student B starts off moving more slowly than student A at 2 seconds, which is what's going to happen, eventually student B's speed is going to increase beyond the speed of student A, and student B will overtake student A. Now, one thing I don't like to do in problems like this is put scales on my graphs right away, because I don't know where that time position point is going to be. However, because I have a 2-second time on my graph, I've already kind of put a scale on this graph. I know where that 2-second mark is. So I just want to note that these graphs are just sketches. Even if I've noted where 2 seconds is, these graphs are still just sketches. I have no idea what the spread of these parabolas are going to be. And one other interesting thing I'm noting on the graph is that, well, student B is starting at 2 seconds. That doesn't mean that the parabola equation is going to just start describing motion at 2 seconds. The equation for that student's parabola actually is going to go back up to the left side of that point. 2, 0 is a minimum of a parabola. Interestingly, later on when I solve for the time where the two parabolas cross each other, there should be 2 intersection points, and I should expect that first intersection point is going to be somewhere nearby that 2-second mark. So I just wanted to put that in there so I know when I get 2 values for time later on as part of the process of solving this, I know what those 2 time values are, what they mean, and which one is going to be relevant for later. Okay, now I'm ready to start solving this by using equations, and the one equation that I have to describe a parabola is this position time with acceleration equation. And this is actually going to be used to describe the motion of both of my students. Now, just sort of inspecting this equation, do we know the original position for both students? Yes, they are both starting at the starting line, which is at 0. Even though one student is starting 2 seconds later, that student's still starting on the starting line. So I can say that the initial position is 0. The initial velocity for both students is 0 as well. They're both starting from rest. We're not given any information in the problem that like one student is starting by coasting across the starting line. We're assuming that both of them are starting from a stopped position. Now, is the only thing that's different between these two students the acceleration? Well, no, because I know that student B is starting 2 seconds later, and how am I going to account for that? Well, it's important for you to remember that the t in this equation is actually a delta t, or a time interval. And when your initial time is 0, then we can just plug in t, and that's going to happen in most problems that we work. So let's just consider student A for a second. Student A's initial time is 0. So the interval from 0 to whatever time t is where they meet in the graph, it's just going to be t minus 0. Okay, so student A's equation is really simple. It's just going to be the position of student A is 1/2 a t squared. But you have to remember that that time is actually time interval. We just abbreviate it by writing t, but what we really mean is delta t, the change in time, the time interval, or the other way to write that is the final time minus the original time, t minus to. And since student B is going to be affected by that starting 2 seconds later, we need to account for that in student B's equation. So instead of just writing t squared, this is going to be t minus to squared. Now notice I'm squaring an expression, and whenever I square an expression, I'm going to need to FOIL the things inside that expression if I need to multiply it out later. We'll have to keep that in mind. Now I have equations for student A and student B. Let's go ahead and list the values that we know. We already talked about how we know that their initial position is going to be 0 for both students. The final position we do not know, but we know something about it. We know that the final position where the students pass one another has to be the same for both students. So I'm just going to note that it's the same value, but it's an unknown value. The original velocity for both students we talked about, we know that that's 0. The final velocity is going to be different for each student, but we don't know what it is. And I'm just going to guess right now, we're probably not going to need final velocity. There's usually one of these kinematics values that we don't find when we solve the problem, unless we're asked like multiple questions about it. If there was a separate question that said, what is the speed of each student at the end, then I would need to know this. I'm guessing though that this is going to be the one variable that we don't have to solve for. Acceleration is different for both students, student A at 0.5 meters per second squared and student B at 0.75. That's why student A was given the head start. And then the time at which the students meet is, again, going to be the same, but we don't know what it is. So I know something about time. I know that it's going to be the same for both students. I don't know what the value is. All right, and now we're ready to start plugging these values into the two equations that we have. We're going to start with student A. That's the simplest of the two equations. Plug in acceleration for student A. That's 0.5 meters per second squared. And then when I simplify this, I find that student A's equation is just 0.25 meters per second squared times the amount of time squared. Very simple, very straightforward. That's going to give me the position of that student. Now I have two unknown variables in that equation, but I have another equation that has the same two unknown variables. So that means I have a system of equations and I'll be able to solve for x or t and eventually for both. Let's take a look at my student B equations. We're going to start off similarly, but notice that I have this time term at the end that's actually a time interval because I'm starting with TO equal to 2 seconds. I'm going to go ahead and plug in the values that I know. And at this point, to simplify further, I'm going to need to FOIL my t minus 2 seconds term. To FOIL that, it's going to look like this, t squared, then it would be minus 2t twice, so it's going to be minus 4t, and then plus 2 times 2 is 4. Okay, and I just kept the labels in there. The labels are all correct. When I simplify the labels eventually, if I were to actually plug in a time and solve this, it would be in terms of seconds squared. And just keep in mind, I'm multiplying seconds squared by meters per second squared. That's going to give me a value in meters. So I'm already just checking and making sure this is going to give me a value that is a position or distance value. All right, the next thing I'm going to do is distribute that 0.375 to each of the terms because it's multiplying again an expression, so I need to distribute it to each. So it's going to be 0.375 t squared minus 1.5 t plus 1.5 when I distribute it out. And the next step is for me to put this simplified expression, this is the best I can simplify this, together with the simplified expression from above in that substitution step, and that'll allow me to solve for one of my variables. In this case, because I have both equations already equal to the position, I'm just going to substitute in for the position value, and that will give us what we need to solve for time. So let me do that, put these two equations together. Notice that because one of them is equal to x and the other one is equal to x, I just made them equal to each other. And now to simplify this, I'm going to subtract 0.25 t squared from both sides. That sets this expression equal to 0. And now I have this expression in a form that's solvable using the quadratic formula. So that's what I'm going to do. I'm going to plug in my quadratic formula values into the quadratic formula to solve for t. And when I simplify this long expression, I find that the time is going to equal 1.10 seconds or 10.9 seconds, and I have to choose which one of these is correct. Now you probably remember that I had that graph that showed that these two parabolas were going to intersect early and later, and the later point was when both students were actually moving and they were actually passing one another, so that 10.9 seconds value is going to be correct. I'm going to take that 10.9 seconds and put it into my table of known values, and in a moment I'm going to use that to solve for my unknown x value. But right now, let's go back and take a look at our two parabolas on this graph. At this point, I'm going to do some scaling on this graph, especially on the x-axis, the time axis of this graph, because now I know some more information about what's happening with time. So I found out that that scale that I drew in before, because I had to draw in some scale, I found out that that's incorrect. Because it only goes up to 5 seconds, and I need something that goes up around 10 seconds. So I'm just going to rescale my x-axis. And that's going to move some points around because I'm shifting things around on the x-axis. Now I know the time in that unknown time position point where the two students pass one another. It's 10.9 seconds. So I'm just going to plot that in the correct spot on the x-axis. I need to shift it over a bit. I also need to shift my 2 seconds point over because currently, because I rescaled it, it's sitting at the wrong spot. So I'm going to move that over to where it belongs. There should be a point at 2, 0. And then finally, I know from the previous work I've done on this that these two parabolas are also going to cross at another point. They're going to cross at 1.1 seconds. And I don't know what the position is that they would cross, but there is going to be a point at 1.1 seconds. So if I redraw my B parabola, it's going to look something like this. And then my A parabola is going to shift too. Because remember, A and B are going to pass one another in the real world at 10.9 seconds. So that means that my A parabola has to pass through that same point that B is passing through. And then also, not in the real world, but as part of the math for this problem, I know that these two parabolas are going to intersect before that 2 second mark at the point 1.1 seconds and then some distance. So my parabola for A has to pass through that point as well. So if I rescale A, it's going to spread out a little bit more and it's going to look like this. Once again, notice that these two parabolas make sense. My student A is going to be ahead of student B at the beginning because student A starts accelerating before student B does. And then when student B starts accelerating, student A is already going faster, but student B is going to catch up, start moving the same speed, start moving faster, and then eventually overtake student A. And that happens at that distance point. Now the question, remember, is whether that distance where they pass one another is before or after 25 meters. Let's find that out now by plugging in my time to one of our equations. It could be either the student A or the student B equation. And it turns out in this problem, the student A equation is way simpler to work with because we don't have that extra time value we need to account for. So what is the position going to be if the time in this equation is 10.9 seconds? Once again, plug in what I know, 1/2 times 0.5, and now I know that that's times 10.9 squared. When I solve this, I find that the x position where the two students pass one another is at 30 meters. Now, as you're reflecting on your response to make sure that you've done everything right, in problems where you have two equations that should equally solve for the same thing, sometimes it's useful to just run your values through that second equation, especially if it's not too hard to do so, to make sure that your value is correct. We should get 30 meters from either of these equations. So a good check on our work is to make sure that we get 30 if we use the second equation as well. So let's go ahead and plug in what we know. And in this case, my time is 10.9 seconds, just like before, except I have to subtract 2 seconds for it before I square it because of the head start. So I'm going to go ahead and do that and solve. And then when I simplify this, I find that x equals 30 meters by this equation as well. And that helps me just to verify and make sure that I solved correctly. I'm just going to plug in that 30 meters to my table. I'm going to express that 30 meter value on my graph as well, because I know it goes into the point where the two students pass one another. Now I have a complete view of what's happening with these two students as they race. Now that I have that complete view, let's see if we can answer the question in the problem. Who will win if the race distance is 25 meters? Well, the students don't pass one another until 30 meters. So that means that student A is still ahead at that point, and student B is just starting to gain on student A, almost passing, but student B needs an additional 5 meters to pass student A. So student A is going to win the race at 25 meters. If the race were longer than 30 meters, student B would have won. And that's a two-part problem involving two moving objects. Another common type of two-part problem in physics is a problem that has one object moving in two independent dimensions. And that's a two-part problem because we have to solve each dimension separately. Now, how does that work exactly? How is it that an object moving in two dimensions has a separate x and y dimension? Let's take a look at a few lab examples to see how this could be so. So in this example, I'm going to roll a golf ball off the table to the right. And we're going to observe its motion as it falls toward the floor. So notice it starts with an initial speed as it rolls along the table, and then it's going to start falling toward the ground as well. Now that happened pretty quickly, but I can show you if you track the motion of the golf ball as it falls, it looks like this. Now what do you notice about this motion? The points are getting further apart. There's obviously some kind of an acceleration happening, but is that acceleration happening in two dimensions or just one dimension? Well, let's take a look at the spread of these points first in the x dimension. And if you look at these points just in the x dimension, you may notice that these points appear to be fairly evenly spread out, whereas in the y dimension, they appear to be getting further and further apart. Let's just take a look just at the x dimension points. Notice that these points appear to be the same distance apart. If you were to just look at this as a motion diagram for an object moving in one dimension, you would say that this object is moving at a constant speed. And that's what happens in two dimensions. In the x dimension, our golf ball is moving at a constant speed if we just look at the x dimension. And then what about that y dimension? If we look at the y dimension separately, we notice that the golf ball appears to be accelerating downward toward the ground. Does that make sense, though, that gravity pulls objects downward, so it's only going to affect objects in the y dimension, and it's actually not going to have any impact on the x dimension motion of an object? And that's what gives the motion of this golf ball as it falls its parabolic shape. So we've observed the golf ball rolling off the table visually. Now let's observe what's happening graphically. And as you look at these two curves on this graph, you may look at that blue curve and say, hey, that looks like the motion path of the golf ball. And you're right, it does look like the motion path, but keep in mind, this is a graph over time, not a map that shows position over position. It's not like the x position and the y position on the x-axis and the y-axis. Time is what's on the x-axis. The reason they look the same, though, is because time goes by at a regular clip, just a regular amount of time between each point. The same was true when the ball was actually arcing off the table. It was covering the same amount of distance at the same rate in the x dimension. So our x-dimensional distance kind of made it look the same way that time makes it look on a graph. And it's important to note when you're looking at a map, you're going to see the x-dimensional position and the y-dimensional position. This is different because we have time on the x-axis. So this is showing us what's happening to just the vertical position. That's what that blue curve is, the vertical position over time. And the red curve is the horizontal position over time. Do you notice that the red curve looks pretty linear and that the blue curve looks parabolic? What that tells us is that in the x dimension, the object is moving at a constant rate, constant speed. In the y dimension, the object is accelerating. Now, if I were to put the actual equations to this, I would see that in the x dimension, the speed is about 1.4 meters per second. Now, I measured the speed of the ball rolling across the top of the table with photo gates, and I measured it to be about 1.3 meters per second. So 1.4 meters per second is remarkably close and well within the bounds of the error that I would expect to have measured between doing video analysis and possibly measuring a little bit incorrectly with the photo gates. So what we're seeing here is that the same speed as the ball was rolling across the top of the table is the speed that it maintains as it moves horizontally through the air, but only if I'm looking at the x dimension alone by itself. In the y dimension, when I linearize the parabola, I see that it's moving downward with an acceleration about double the slope of this graph. So double the slope of this graph is about 12 meters per second squared. I measured the acceleration to be about 12 meters per second squared toward the ground. Now again, that's off by a little bit. We expect acceleration to be around negative 10 meters per second squared. Negative 12 meters per second squared is probably including a little bit of error in the way that I measured, especially the video analysis step, because video analysis, it's really easy to accidentally click a little bit too far down consistently on the ball and make it look like it's accelerating toward the ground faster than it should be. Let's take a look at another demo that demonstrates the independence of the x and y dimensions. In this video, we're going to see that this cart is going to be rolled at a constant speed toward the right. And when it passes that metallic strip, that black metallic strip, a ball is going to be launched from the cart up straight into the air. What's going to happen to that ball that's launched into the air from the cart? Let's watch and see what happens. So here the cart's rolling, ball launched. Look where it lands. We're going to watch the same thing in slow motion. Okay, if we were to graph this out, this is what the map of this looks like. This is just showing the position as it travels horizontally and vertically. And notice that the ball moves up into the air. It's decelerated by gravity clearly in the y dimension because it moves upwards, more slowly, comes to a maximum, and then starts to fall back downward again until it lands back in the bucket from where it was launched. But what's going on in the horizontal dimension? Is it accelerating horizontally? If it were accelerating in the horizontal x dimension, there's no way it would land back in the bucket because the bucket's moving at a constant speed without an acceleration. If the ball was accelerating, it would move either forward or behind the bucket, but it lands back in the bucket. The x and the y dimensions are completely independent from one another. Here's the kinematics in the x dimension. Notice that this is a linear graph showing that this is pretty much a constant speed of 0.46 meters per second. And this is what's happening in the vertical dimension. The ball is going up into the air and being decelerated by gravity. And then eventually it actually falls back down again. But I was only able to get good points in the y dimension for this much of the graph. And if you look at this, the acceleration due to gravity was 5.18 meters per second squared. That's really close to negative 10 meters per second squared, which is what we would expect due to gravity. All right, let's take a look at one more demo. In this case, we're going to launch these two balls from the same height and let them hit the floor. One of them, the one on the left, is going to be dropped straight downward, and the one on the right is going to be launched outward. Poked at by the rod that you see in the picture. But essentially, they're going to be launched from the same height at the same time, one of them falling straight down and one of them propelled to the side. Let's see what happens to these two objects under these conditions. Notice that they hit the ground at the same time. It doesn't matter that one of them has an x velocity and the other one doesn't. That affects that one's moving in an arc and the other one's not, but vertically, they both hit the ground at the same time. Gravity accelerates them toward the ground at the same rate, and therefore it doesn't matter whether an object is moving horizontally or whether it's just dropped, it's going to fall with an acceleration due to gravity the same as it would either way. And if it's moving horizontally, it's just going to continue moving horizontally at a constant speed unless for some reason something causes it to accelerate. But in this case, nothing caused any of these objects to accelerate horizontally. Gravity caused them to accelerate vertically, and the two dimensions are independent of one another. So how does this affect our problems that we work? How can we work a real-world problem with acceleration in one dimension, not in the other dimension, but an object moving in both dimensions? Let's consider this problem. Two students are playing catch with a baseball in an open field. One student pitches a horizontal fastball at 36.7 meters per second. The ball is launched 1.2 meters above the ground horizontally. The other student completely misses the catch. How far will the ball travel before it lands? And then a second question. This is a second part of the question, but keep in mind that each part of this is going to be a two-part, two-dimensional question. So the second question is, if this fastball were pitched horizontally during a game, how high would the ball be when it passes home plate 14 meters from the pitcher? Let's dive into this problem.
I'm going to start by making a diagram of this problem so I can visualize what's happening. So here's my pitcher, and then here is the ball at various points over time during its flight. It's going to look just like the previous examples where we had an object being launched horizontally, and then over time we could see that it was accelerating downward, but then moving horizontally at a constant rate. Another way to visualize this is one dimension at a time. And that's actually how we're going to work this problem, one dimension at a time. For example, if I just look at the x dimension, I can look at these points here, all in a straight line across in the x dimension. And I notice that in the x dimension, there's no acceleration. If I were to look at these points just by themselves, it would appear as if it's an object moving in a straight line at a constant speed. The rate of change of position over time is the same, and that's why these points are all evenly spread. However, if I look at this in just the y dimension and put everything in a straight line in the y dimension, notice that you see that the ball is accelerating toward the ground in the y dimension. Now, like I said, I split this into the x and y dimension. I'm going to solve one dimension at a time. My next step is to make a list of everything I know in the x dimension and the y dimension. Notice this looks similar to the tables we were making for two objects, where we would list everything we know about one object and everything about the other object. Here, we're splitting the dimensions to make this list. Notice once again that there is something similar between the x and the y dimension. Time is going to be the same in the x and the y dimension, so I'm only going to have to find one variable to describe the time. But let's go ahead and list what we know. Do we know the original x position of the ball? That's going to be at our reference distance, reference position, so I'm going to set that to 0. The x position when the ball leaves the pitcher's hand is 0. The y position is going to be 1.2 meters above the ground, and then the ball falls from there. My final x position is unknown. That's actually what the problem is asking for, so that's something I have to solve for. What about my final y position if the other student misses the catch and the ball hits the ground? That other y position is going to be 0 at the end of the problem. The original velocity in the x, well, I'm given 36.7 horizontally, so 36.7 is going to be the initial x velocity. What about the initial y velocity? Its initial velocity toward the ground if it's thrown horizontally. Well, it's the same as if it were dropped. Its initial velocity is going to be 0 in the y dimension, vertically. It's not being thrown upward or downward, it's being thrown horizontally. And then my final velocity in the x dimension is going to be the same as the initial velocity because velocity in the x dimension is constant. In the y dimension, we don't know what the final velocity is, and I'm guessing we're not going to need to find it for this problem. Unless we needed to calculate something else, we probably don't need final y velocity here. The acceleration? Well, in the x dimension, because it's moving at a constant rate in the x dimension, the acceleration is 0. In the y dimension, acceleration is acceleration due to gravity. That's what's pulling it downward. And then the time that this all takes, I don't know, but the one thing I do know about time is it's the same for both dimensions. Now, as I look at this, I see that I have an unknown in each column, and then time is unknown for both columns. But I also note that I probably don't need the final velocity. I'm not being asked for final velocity anywhere in this problem. So I'm not going to worry about that unknown. The two unknowns I'm looking for, I'm asked to solve for in this first part of the problem are the distance. And in order to find that distance, I'm going to need the time. So I don't know more in the x dimension. There's more that is unknown in the x dimension than in the y dimension. And therefore, I'm going to start with the y dimension to solve this problem. We'll see how that goes for us. So in the y dimension, I'm going to be looking for the time from the distance. Do I have an equation that includes distance and time with acceleration? Well, I sure do. Y equals the original position plus the original velocity in the y dimension times time, plus 1/2 acceleration in the y dimension. I could replace that with the letter g. And actually it would be negative. I'd have to say negative g times time squared. Okay, what goes to 0 here? Well, I don't have an initial y velocity, but I do have an initial y position of 1.2. So I'm going to go ahead and plug in everything that I know here. I know the original position is 1.2. I'm going to put the final position as 0 on the left-hand side of the equal sign, and then acceleration is negative 9.8. When I simplify this, I'm going to subtract 1.2 meters from both sides, and then I'm going to multiply 9.8 by 1/2. That gives me this, and then I know that t squared equals negative 1.2 over negative 4.9, or t equals the square root of that expression. It's always a good thing when the value under your radicand is positive, so it's good that we're dividing a negative value by a negative value to get a positive value. When I actually solve this, I find that the time is 0.49 seconds. And that makes sense. This ball is going to be accelerated toward the ground very quickly. If it's dropped from 1.2 meters, it's not going to take very long for it to reach the ground. I'm going to go ahead and plug that value in for time as something I know in my chart. And now we're going to move from the y dimension over to the x dimension. What do we know in the x dimension? Well, I'm going to try to use that same kinematics equation because we have position and time, but my acceleration is 0. So that's going to simplify this equation an awful lot. It's just the equation for average velocity, the slope of the position time graph equation. And this is pretty easy to solve. So I'm going to plug in what I know. I know the original position in the x dimension is 0. That's what we set as our reference point. I know the original velocity and the final velocity are the same. So I'm just going to plug in for Vx, 36.7 meters per second, and time is 0.49 seconds. I simply multiply these two values together, and that tells me that the ball is going to hit the ground 18 meters from when it leaves the pitcher's hand. 18 meters is my final answer for this problem. All right, what about the second part of this problem? Am I able to figure out if this fastball were pitched horizontally, how high is it going to be off the ground when it passes home plate? Now, how is this problem different? Well, I'm going to have the same initial speed and the same initial height above the ground from where the ball is thrown, but it's not going to hit the ground anymore. We're only observing until 14 meters from the pitcher. There's a specific distance, and at that distance point, I wonder what the height of the ball is. It's not going to be 0. And it's not going to take the same amount of time as we calculated in the previous problem either, because it's before the time it would hit the ground. So we're going to have to come up with a new set of knowns and unknowns. Some of them are going to be the same, but let's just think these through again. What is my original x position? Well, that's still going to be 0. And my original y position is still going to be 1.2 meters. I'm starting from the same place. My final x, though, is 14 meters now. Before it was unknown. Now I know it's 14 meters. And my final y position is the unknown. And that's the unknown that we're looking for. We're solving for that final y position. My original velocity in the x dimension is still 36.7 because I'm throwing it at the same speed. The original velocity in the y dimension is still 0 because I'm throwing it horizontally. So it doesn't have a vertical initial velocity. And once again, I don't know the y velocity at the end, but I don't think I'm going to need it in this problem either. And just noting that the final x velocity is the same as the original because it's moving at a constant speed in the x dimension. Acceleration in the x dimension is still going to be 0, and acceleration in the y dimension is going to be negative 9.8 still. and the time is still an unknown, but once again, I know that time has to be the same in both dimensions. If it moves for a certain amount of time in the x dimension, I'm going to have to use the same amount of time in the y dimension for this to make any sense. Okay, now looking at my list of knowns and unknowns, this time I know everything in the x dimension except for time, and my unknown is in the y dimension. So I'm going to start with the x dimension first and calculate how long it would take if the ball was moving at a constant speed of 36.7 meters per second for it to go 14 meters. That's an easy problem to solve. Once again, acceleration is 0. My initial position is 0 in the x dimension. So all I have to do is plug in my known x value of 14 meters and my known velocity of 36.7 meters, then solve for time. Well, time is going to be 14 divided by 36.7 if I rearrange that, or time is 0.38 seconds. And that makes sense because it's going to be less time than the time it would have taken if I just let this hit the ground. I'm going to go ahead and plug that 0.38 seconds into my table. And now we can solve in the y dimension because we have that key piece of time information. The y dimension equation is going to be the same as the last time we solved in the y dimension because we're still solving position time in the y dimension, but this time we're looking for something different. We're looking for the final y position, and that's fantastic because that's the value that's on the left-hand side of the equal sign. This equation was meant for calculating that final y position. So I'm just going to, first of all, cross off things that are 0. My initial y velocity is 0, so I can cross that off. And then I can plug in values that I know. My initial y position is 1.2 meters, and my acceleration is negative 9.8. I'm just going to simplify that negative 9.8 right away and make it negative 4.90, just like before. And if I go ahead and solve this expression, I find that the position above the ground is 0.49 meters, so almost 0.5 meters. And I'm just going to go ahead and plug that into my table because that's the value that I solve for. And that makes sense too. I would expect it to be somewhere below 1.2 meters. And because the ball is accelerating toward the ground, a greater proportion of that 1.2 meters is going to be lost later in time as the ball speeds up toward the ground than near the beginning. So it makes sense that it will have fallen maybe about, half of the way, a little more than half of the way, even though it's more than half of the time has gone by before it will hit the ground. All right, now we've solved two different two-part problems. We solved a two-part problem in one dimension because we had two different objects that were moving with one-dimensional motion, and we solved a two-part problem with a single object moving in two dimensions. By now you should understand that the x-dimensional motion is independent of y-dimensional motion, so you can split them apart and solve one dimension at a time. In each dimension, we know that the time variable is going to be the same. That's what ties the two together, even though the positions and velocities and accelerations can be different from one another. And that's how you solve a two-part problem that's one object moving in two dimensions.